Finally, we are ready to introduce our first Sobolev class on general metric measure spaces, the so-called Hajlasz-Sobolev functions. The setting again is a metric space equipped with a Borel regular measure. The class of functions will be defined for the exponent between 1 and infinity, excluding infinity. So what is the definition? It's quite simple. So M1p of x, which is our Sobolev space, is the set of those functions in LP. You integrate power p of u against the measure mu, such that there exists another LP integrable function on x with g bigger than or equal to 0, such that the key inequality, the part which gives g as the derivative of u, so ux minus uy is less than or equal to the distance of x from y multiplied by gx plus gy, such that this inequality holds almost everywhere. And that's the definition. We have to explain this almost everywhere because that is very critical. So almost everywhere means there exists some null set, set in X with measure equal to 0, such that a property holds. We say a property holds almost everywhere. Well, in this case, let's say such that this star holds for all x in x minus this null set, and all independently all y in x minus n. So it's not the competing notion could be that it's a null set in x cross x, because these tuplets the inside that's not what is meant. So almost everywhere is simpler here. So it's just a null set in the original x. Once you don't pick either of x or y from that set, you have the inequality. So that is what is called the Hajlasz-Sobolev class, and G is often called the Hajlasz gradient of the function u. So if you divide the inequality star by dxy, this division is familiar from the definition of derivative from calculus 1. If you let y converge to x, this converges to the derivative, and that's an analogy to keep in mind. But there are many subtleties here. We will see later, for example, that this g is actually a global object and seldom equal to 0 actually, even when u is constant on a part of the space. Okay, so we have discussed a lot what we even want from a Sobolev class on a metric setting, what deserves to be called Sobolev functions, and here are some indications that this is indeed a natural and good definition for abstract Sobolev spaces. The first observation is that if omega inside Rn is open and u belongs to W1p of omega, the classical Sobolev Sobolev space defined through weak partial derivatives, then there is a constant which only depends on n, such that g of x defined by the maximal function, so this Cn, or just C, okay, Cn maximal function of the gradient of u. This is again classical gradient. You take absolute value, it's a real valued function. Now you take the maximal function and then you evaluate it at the point x, so that gives you your function gx. So up to this constant is just the maximal function of the gradient. So the claim is that when you have a function in the classical Sobolev space, then a multiple of the maximal function of gradient does satisfy star. So the function u belongs to m1p of Rn equipped with the standard distance and the Lebesgue measure. And this explains also the notation m for the space m1p, because m comes from the maximal function. Now, I hope you know what maximal function is. The key property we have here is that maximal, so by choice of u, gradient u itself belongs to LP, and the maximal function of an LP function is again in LP, modula requiring that PB is strictly bigger than 1. So P equal 1 is always a bit tricky when it comes to Hajlasz class, exactly because the maximal function is bounded only LP to LP if P is strictly bigger than 1. And the reverse of this is also true in many domains. So the follow-up fact is that in smooth domains, or maybe even in Lipschitz domains, M1p is just equal to W1p of omega. And that is probably the strongest justification for this space, that although defined through very abstract machinery and with no use of partial derivatives, with no use of the coordinate system in Rn, without relying on any Euclidean space, we have constructed a space which does, at the end of the day, happen to be equal to the original Sobolev space. So that gives a characterization of the Sobolev functions in the Euclidean setting, at least for nice enough domains, that does not rely on any Euclidean structure. And that is a success already for this space. Okay, so that's probably also historically this was in reverse order that Hajlasz realized that we do have this, and from there it was natural to generalize it to all settings. Okay, so we had the previous video focused completely on properties of Sobolev functions in the Euclidean setting, what we expect from a Sobolev class in the metric setting. And here's some of the things that that do hold on this space. Before that, we must define actually a norm on these functions if we hope to turn them into vector or Banach spaces. The norm that we define for a function in M1p of x is, well, u itself is an LP function by definition. Okay, and then it has a Hajlasz gradient, which is again an LP function. But G is not, by our definition, uniquely defined for U, there could be multiple G satisfying this. For example, if one G satisfies the inequality, you can multiply it by 5 and it still satisfies it. So you put infimum over all such G. So infimum of G that are Hajlasz gradients of U. So with this definition, you can show that this is actually a norm. And now the theorems and results that I will give without proofs that tell us why this class M1P has many nice properties of the class W1P of the Euclidean setting. Number one is that M1P is a Banach space. By the way, we had a separate video completely focused on references and literature on this theory, and that makes me sad, not happy that I don't have to refer each time back to papers. But these are from a paper of Hajlasz published in '96, but the work was actually earlier submitted already in '94, and this is a solo paper by Piotr Hajlasz. And many of these results that I'm mentioning here were already proved in that original paper. So even for the case 1, okay, let me mention that this is emphasize that that was just an example to compare it in the Euclidean setting to W1P. Now we are back to the abstract setting of metric measure spaces. So M1P is a Banach space, and that was our first property that we expected from any Sobolev class, where we also mentioned why it is important. For example, we want to solve PDE or calculus of variation problems, and the go-to method is always to find sequences, produce convergent sequences out of them, and continue from there. And if you hope to produce more easily convergent subsequences from sequences without too much restriction a priori, you need a Banach space. Okay, and the second property that equality in the Sobolev extension domains holds that equality between W1P and M1P, and that's actually an important theorem that I gave the name facts, but it's actually an honest theorem. So the other one is that functions in M1Px satisfy the Poincare inequality, and more specifically the PP Poincare inequality, which is stronger than 1P. And what does that mean? It means that okay, I'm also consulting the book by Heinonen, Lectures on Analysis on Metric Spaces, which is a very, very famous book and very beautifully written, by the way. I really recommend reading it. One thing I love about this book is short chapters, which just encourage you to read them in one sitting, or it's beautifully written without going into too much detail. It gives you a clear picture of what is happening, and then good references if you want to go deeper into details. So my notation and terminology are based on this book, which in some instances could be outdated, but we are not probably that concerned about sharp results at this point. So anyway, what it means for this space to support Poincare inequality. First of all, there's this condition that we want the measure to be finite. Okay, that's needed. and the p is not restricted here, could be also 1. So meaning that if u is m1px, then integral of u minus average of u over x to the power p d mu is bounded by 2 to power p, so we even know the constant here, diameter of x to power p, integral of g to power p over x d mu. For every, remember g is g bigger than or equal to 0, that is, well, not d, but a Hajlasz gradient. Of u. So for any pair of function and its derivative, well, derivative quotation mark, we have the inequality. Notice that this again is non-trivial only if diameter is also finite. So technically we are saying that when diameter of x and measure of x is finite. But still it covers a lot of instances also if you are in a larger space. When you just restrict to balls, you have finite diameter and hopefully finite measure as well, so it's not too restrictive after all. But yeah, this is an important thing to keep in mind, especially in comparison to the Newtonian space that will come much later, where whether a Poincare holds is actually a big deal, a question. So it's some spaces do have it, some spaces don't. But here we're saying that in all spaces, in almost all spaces, it's just built into this definition of M1P that they do satisfy a PP Poincare inequality. This can also later show why, for example, for certain subsets of Rn, M1P is not equal to W1P, as there are some examples given in Heinemann's book, quite easy ones based on the slit ball minus 1 radius. Just because we know that these functions satisfy a Poincare and maybe not all satisfy Poincare back here, we can rule out this equality for certain open domains in Rn. Okay, another property, again, theorem 3, whether we have Poincare inequality, again, was in the list of properties that one expects from Sobolev functions, or one could expect from them. The next one, again, very different from the Newtonian class, is that Lipschitz functions are always dense in the space. So again, range of p is p greater than or equal to 1. Then Lipschitz functions are dense in M1P of x. So what is the meaning of this density? Well, actually this is twofold. Given u in M1P of x and epsilon positive, the error tolerance, so there exists a Lipschitz function. We use phi from x to r such that, so we are given a Sobolev function. We want to find the Lipschitz functions that approximates this. One obvious way of measuring approximation is that u minus phi. So Lipschitz functions are in the Hajlasz class because you can put the Lipschitz constant for the upper gradient. So this dxy. And we know that this is already less than just the Lipschitz constant of the function phi. You don't even need to add two of them. So they are always in the Sobolev class. So we have two functions in the Sobolev class we can subtract. It's a Banach space. That's another one. And we look at its norm, which we defined above. So one approximation is that we require this to be less than epsilon. But we can actually add more. That the measure, that u and phi are actually equal. They coincide on a huge set. So the set of all values where u of x is not equal to phi of x is less than epsilon. So this is much stronger because it doesn't say that values of u and phi are close. This is saying that they are exactly equal, except for a very small set. And these are known in literature as Luzin properties, or we can say this is a Lipschitz-Luzin property. If you have followed my videos on area or coarea formula, you definitely have seen this, where starting with the Lipschitz functions, you can approximate it by a C1 function in this sense. Okay, and this is again a big deal that Lipschitz functions are dense in the space. When in other versions of Sobolev spaces on metric measure setting, this is not a given. And why is this nice? Because as Heinonen says in the book, Lipschitz functions are the smooth functions of the metric world. So if you like C-infinity functions in Euclidean space, then you should love Lipschitz functions on a metric space. They are very nice. They usually belong to many of the Sobolev spaces that we define. Whether they are dense is a different question. And also there are many of them. So this little remark, there are many Lipschitz functions on any metric space. And also, we don't need a measure to talk about Lipschitz functions, by the way. Why? Well, fix a point, x naught, and look at the function that measures its distance to another one. This is one Lipschitz function. And unless your space is a finite set of points, this is an interesting function. Okay, so let's call this phi 0. Now you have found many Lipschitz functions by changing x naught into r, but then you can also change it. You can do another Lipschitz, any Lipschitz of r to r, you can compose it with this phi naught and produce new ones. Also, this shows that the Sobolev class is not trivial because it contains the Lipschitz functions, and we saw that there are many Lipschitz functions. So this space is always non-empty and non-trivial. Okay, and next one, maybe this is like a heads up to future remark type of observation, that if u in M1p of x is continuous, that means it has a continuous representative as a measurable function, and measure mu is doubling, then we can require this inequality star to hold everywhere by redefining G on a set of measure 0. So the definition of the Hajlasz functions was that u minus uy bounded by distance xy, gx plus y. We required that this hold for all x and y that are not picked from a certain null set. But under this assumptions, we can change g to another one and then require that this inequality holds everywhere. So, and this change means only redefining on a null set. And also when we later define the Newtonian space, we will see that that space n1p of x usually contains m1p. I mean, always contains this, and it very easily happens that this is strict. For example, if you have the snowflake with no rectifiable path, this will be just all of LP. But this is those LP for which there is another LP function G satisfying this. So this is much smaller, much refined. You have no Poincare inequalities for this, but you do have for them. So that's also an example showing why this class can be better than the larger Newtonian class that we will define later. Okay, and last remark, non-locality. So we said that G is Hajlasz gradient of U, and heuristically it's a derivative of U, but it has also some properties that are very different from what we are used to expect from derivatives. Suppose this is your space X. You can even imagine it's a subset of R2 with the Euclidean distance and the Lebesgue measure. Suppose you have some function u from x to r, and u is constant equal to 0 here. Well, let's say a here, because then you might think that there's anything special about. Okay, and a is not equal to b. Then the function g cannot be actually 0, is not constant 0 on these two open sets. So let's say E1 and E2. So these are open subsets of omega on E1 union E2, because, well, if you pick 2 points, one from E1, one from E2, then what you have is that a minus b is u of x minus u of y, and this should be less than distance of xy, which is a non-zero number, times g of x plus g of y. So if we had g constant 0 on this union of these sets, then this side would be 0, this side non-zero, and we would be in trouble. And there is a very nice about the half-page discussion in Heininen's book about well, natural ways one could think of eliminating this problem by requiring, for example, in the definition that even from the beginning you require that this holds at a local scale, not like for all x and y that are arbitrarily far away. But then there are exercises there showing that this actually does not alleviate the problem in any way. And the message I got from there is that it's quite hopeless, and this G will always have this global nature to it, which is probably also validated by the fact that we have the Poincare inequality all the time, and which we know this Poincare inequality is very restrictive also on the local and global geometry of a space. So there you go. So we have our first space that, because of the properties, the theorems that I mentioned, deserves to be called a Sobolev class on a metric measure space. If you want more details, if you want to see proofs of, say, y in the Euclidean setting, this is equal to that, where on earth does one prove that the maximal function provides a Hajlasz gradient for the classical Sobolev spaces. If you want to see proofs of these, let me know in the comments. Otherwise, I will assume that this level of generality is good enough, and that more technical details probably will distract us from our main goal and have us struggle in making any fast progress. Okay, thanks a lot, and see you in next video.